Hello everyone and welcome to this presentation. My name is Victor Férat and I am a third-year PhD student in Christophe Michel Labs in Geneva. Today, I have 10 minutes to introduce you to Pycrostates, a new Python library that can be used to study EEG microstates. The story behind this library is that I'm currently running a neurofeedback study on EEG microstates, and I implemented a lot of different functions and classes that are useful to run such analysis. I decided to pack them and to put them all together and create a Python library to allow other people to run such analysis offline or online. Today, I will try to show you the main functions that are enabled by microstates. And for that, we first need to load some data. So to do that, Pycrostates includes a library called dataset, which allow you to directly download some preprocessed EEG dataset for the brain body dataset available online. So here we have a piece of code that allows us to load a subject by ID, and we can either load eyes open or eyes closed condition. Pycrostates is built on top of MNE and use its main classes to run the analysis. So for example, here we will use the MNE Python functions to load the datasets and to preprocess it in different ways. Here, for example, we crop it and we pick only EEG data. And we also create some epochs to show you the different possibilities in Pycrostates. So first, what is EEG macrostates? So EEG macrostates is a way to decompose your EEG signal into different segments of data. So we can take this metaphor where we have an image and we want to find the main color of this image. For this, we can use the modified ModKMeans algorithm that will find the centroids of the colors. Once we have these colors, we can transform our image into another image that only uses these colors. As you can see, we lose a lot of information, but the general idea of the data is still here. We can recognize the image. For EEG data, it's quite the same. For each instant of your EEG recording, you can display your data as a topomap. So you can have an EEG recording that is a succession at each sample of different topomaps. What we are doing is that we are trying to find some topomaps that best represent our signal. Once we have found these topomaps, we can use them to decompose the time series of the signal into a succession of states defined by these topomaps. So for example, here, each color represents one of these topomaps, and we can say that each topomap has a certain duration, appear a certain number of time, and have a certain explained variance. So Pycrostates allow us to make this decomposition thanks to a modified version of the K-means that use absolute spatial correlation as a metric for distance. So we can instantiate this function as we can instantiate a SKRN model by creating it. Once we have created this instance, we want to feed some data in order to compute the main topography. So the algorithm behind this decomposition was first written by Pascal Marquis, Christophe Michel, and Dr. Lehmann, and is, as I said before, a modified version of K-means. This algorithm takes as input an EEG recording, or if we look at it in another way, as a lot of topographies, and find the car centroids of these topographies. This algorithm ignores the polarity. So there is no difference if we have blue, like less active regions, or red, more active region here, or if we switch the polarity. In Pycrostates, to use this fitting, we can use our modified K-means and fit it with an instance from MNE, a row instance or an epoch instance. By default, this will only pick EEG data. So we have to make sure that we don't use miscandelous data such as EEG. Like most of MNE function in the API, we can only select a subdivision of recording with tmin and tmax in order to have only some period of the recording. And we can also exclude bad regions with the reject by annotation parameter. This function during fitting will fit the K-means with a lot of iterations, a lot of initializations by default 100, and keep the iteration with the highest explained variance. In our implementation, we use parallel processing that can be used by using the njob parameter. So each iteration, each initialization can be run in parallel on the computer to faster the process. Once the model is fitted, we can use the plot function to display our results. There is additional methods that can be used to rearrange our data. So, for example, we can use the reorder cluster to reorder the order of the topographies. Then, if we want, we can give name to those topographies to match the literature. Usually, those states are called with letters A, B, C, D, F, and sometimes more. Finally, we can also invert polarities. As we said before, in microstate analysis, the polarity has no impact, just for display. So if we want, we can, for example, invert the polarity of the state D here. Once we have these main topographies, we can also use this on epoch objects. Once we have these main topographies, we want to create the segmentation. This was also introduced in the same paper by Pascal Markey and is using a smoothing algorithm that also allows us to reduce noise in the data. So basically, we have our EEG data, we have computed, thanks to the fit method, our main topographies, and now we will predict the topography, the segmentations, thanks to those topographies. In order to do that, we can use the predict method from our algorithm that take an instance, and we can still reject bad epochs of a channel. In this case, they will be ignored for all during the next steps of the process. The smoothing algorithm allows us to smooth temporarily the signal. We can use a specific window size, and we can also reject segments that are too small, that are maybe due to noise, and also reject edge segments that are the segments that are at the beginning and the end of our recording, because we cannot know what was happening before or after. The output of this predict method is a segmentation object that can be plotted, as we can see here. During the process, Pycrostates will output some info saying which parameters were used that can be reported on the paper. This process is also enabled for epoch objects, and we can have a plot of epoch segmentation. Once we have our segmentation, we can use the compute parameters method to compute different parameters on this segmentation. For example, for each state, we can have the mean correlation, the global explained variance, the occurrence of these states, the time coverage of these states, and this for all the states. If we want, we can use pandas or Python ecosystem to put it as a table and run some statistical analysis if we have several subjects. Here we also have some parameters to mention the distribution of this matrix, so to have a better understanding or control of what is happening during the segmentation. So, for example, here I'm displaying the distribution of duration of microstate C in the recording. Here it was the simplest way to analyze and to compute the segmentation, but we can use some preprocessing step to improve the segmentation. For example, we can use the resampling here that is able, thanks to the resample method, that you create a resample from your EEG recording. Here we create 5 resamples, each covering 20% of the original recording randomly, and we can fit for each of these resamples the K-means algorithm to see the stability of our results. We also extract GFP peaks that are the samples where the global field power is the highest, and they are known to as the less noisy part of the recording. So we can only use this part of the data to fit the algorithm. These peaks can be extracted thanks to the extract GFP peak methods. And then we can use these peaks here to fit our modified K-means and compute better topographies. Finally, we can evaluate the quality of our clustering thanks to the metrics library from Pycrostates that allow us to compute different cluster quality metrics, such as the silhouette index, the Kalinski-Arabs metric, the Dune metric, and the David-Bolton metrics. We can then create a loop for different number of cluster centers, different number of topographies, to see which number fits the best to our data. Here, we can see that for each different number of clusters, we have different index scores that can help us to choose the best number of states to use in our analysis. So I would like to thank you for listening to this presentation. If you have more questions, you can go to our GitHub, to our documentation online, or join me by email. In this presentation, I tried to show you the main function of our library, but don't hesitate to explore it more, especially with this documentation links. Thanks for your attention, and see you another time.